Getting a robot to reliably navigate the real world. It sounds simpler than it is, doesn't it?
Oh, definitely.
You'd think you could just, tell it, go there. But getting these machines around complex, messy environments, it's a huge challenge.
Absolutely. They often need like perfect maps, precise locations,
Yeah.
which just isn't reality.
Right. And the usual way. Training them involves tons of super expensive real-world data collection.
Yeah, and then trying to get that robot trained for one place or one body type to work somewhere else, or as a different kind of robot. That's been, well, the dream, really.
It's an adaptability problem.
Exactly. Generalization. Think about a delivery bot hitting unexpected clutter, or your robot vacuum in a new apartment layout. Future robots need to handle endless, unique situations.
They can't be pre-programmed for everything.
No way. So the big question is, how do we make robots that learn to navigate effectively, across all sorts of real-world places?
Okay, let's dive into this because we've got some really fascinating research here that seems to be hitting this exact problem head on. You shared a paper with us. It's called NavDP, Learning Sim-to-Real Navigation Diffusion Policy with Privileged Information Guidance, Kai et al., 2025.
That's the one.
And the core idea, it seems, is training robots entirely in simulation.
Right.
And then, bam, they can work in the real world, even on different robot bodies. No extra real-world training. They call it zero-shot transfer.
Yeah, zero shot, which is pretty ambitious.
So the key insight, by giving the robot sort of perfect vision in the simulation, they teach it the fundamentals much faster. Better than messing with real-world data.
Precisely. And the way they do it is really innovative. This system, NavDP, Navigation Diffusion Policy, it's got this clever two-step process.
Okay.
First, it uses the diffusion process.
Yeah.
Think of it like brainstorming lots of potential paths all at once.
So not just one route, but a whole cloud of possibilities.
Exactly, a whole range. And then step 2, there's a critic function.
A critic.
Yeah, it looks at all those brainstormed paths and picks the one it thinks is safest.
Yeah. And it does this just based on what the robot sees right now, locally.
Yeah, based on its sensors at that moment. And both parts, path generation and safety check, are handled by this shared policy transformer. You could call it the robot's navigation brain.
Now, this is where it gets really interesting for me. They use privileged information during the simulation training. What does that actually mean? How does that help?
Okay, so privileged information means that inside the simulation, the robot knows everything. It has the complete map, the full layout, perfect knowledge.
Okay. Like a cheat code in a video game.
Kind of. And this lets them generate really high-quality training data. They know the perfect collision-free paths.
Right.
And they also know why other paths are bad, why they'd cause a crash.
Gotcha. So it helps train both parts, the part making the paths and the part judging them.
Exactly. It helps the diffusion policy come up with good options, and it trains the critic to be really good at spotting the safe ones versus the dangerous ones.
And this whole simulation training thing, it's way faster than using real robots, right? The paper mentioned a huge speed difference.
Oh yeah, massive. It's like a huge advantage. It completely flips that bottleneck of collecting real-world data, makes the whole thing much more scalable.
How much faster are we talking?
Their simulation pipeline is about 20 times faster than trying to get the same experience with physical robots.
Okay, 20 times.
And that speed let them create this enormous data set, 363.2 kilometers of simulated movement.
Kilometers.
Yep. Across over 1,200 different virtual scenes. That sheer volume is key for the AI learning a strategy that works almost anywhere.
Okay, so they train the whole system on this massive virtual data set, and then it just works. On real robots, different kinds, in places it's never seen. That feels ambitious.
The results are genuinely remarkable, though. They show state-of-the-art performance and really consistent generalization across different robots.
Like what types?
They tested it successfully on a quadruped, a dog-like robot, a wheeled one, and even a humanoid robot.
A humanoid, okay.
And these robots navigated real-world indoor and outdoor spots without ever being trained in those specific locations. Wow. There was also something about a preliminary attempt using Gaussian splatting. Sounds complex.
Yeah.
What is that? What did it do? Right, Gaussian splatting. It's a newer technique, basically, for making super realistic 3D models of real places from photos, like creating a photorealistic virtual copy of a real room or street.
Okay.
So the researchers experimented. Could showing the robot these ultra-realistic virtual scenes boost its real-world skills even more? They made these real-to-sim environments using Gaussian splatting.
More realistic simulations based on real places.
Exactly. And then they did a little bit of extra training, fine-tuning, using data from these reconstructed scenes.
And how did that turn out?
Surprisingly well, actually. This
Yeah.
small extra step gave them a big boost, a 30% jump in the navigation success rate in real-world tests.
30%, just from a bit of fine-tuning on these realistic scenes.
Yeah. And importantly, it didn't seem to hurt the robot's ability to generalize to totally new places it hadn't seen, even in simulation.
Interesting. So it suggests this could be a way to bridge that sim-to-real gap even further.
A very promising direction, definitely.
But why only a little bit of that data? You said too much could hurt generalization. What's the trade-off there?
Well, the thinking is, if you train too much on hyper-realistic copies of specific real places, the robot might start to overfit to the tiny details of those places. It might become less adaptable, less able to handle the variations in completely new, unseen environments. So finding that balance seems key.
Okay. So let's dig in a bit more. Yeah. How does this all actually work under the hood? How does that diffusion policy create these potential paths?
So the diffusion policy basically learns to undo noise. In the simulation training, they start with a perfect path. Remember, they have the whole map, the privileged info.
Right.
Then they deliberately add randomness, noise to this path over several steps. They mess it up. The policy learns to reverse this process, to denoise it. It learns how to get back to the original safe path from the noisy version, using just the robot's current sensor input and its goal.
Like cleaning up a blurry photo, but for movement paths.
That's a great analogy. And because it learns this denoising, it can generate lots of plausible, slightly different, safe-looking paths when it's actually navigating.
Makes sense. And then the critic comes in. How does it decide which path is safest, just based on what the robot's camera sees right then?
The critic is also trained in simulation, specifically to judge the safety of a short chunk of path ahead. It learns to connect what the sensors see the RGBD camera input with the chances of hitting something if it follows that path segment. And crucially, during training, the critic has also shown bad examples, paths that definitely lead to collisions, again, using that privileged map knowledge.
So it sees good paths and bad paths.
Right. This contrastive learning, showing it right and wrong over and over, helps it develop a strong sense of safe versus dangerous, even without the full map in the real world.
So it gets a kind of intuition for safety based on visual cues and what happened in the sim?
Precisely. And because the critic uses the same underlying brain, that policy transformer, as the diffusion part.
Ah, they share intelligence.
Yes. It benefits from the same learned understanding of the world and the robot's limits.
Yeah.
So it can make good judgments about which generated path is likely safest out there in reality.
And what about the fact they trained it on different tasks at once, like going to a point or towards an image or just exploring? How did that help it generalize?
Oh, that multitask training is super important. By making the same network handle different goals, the robot learns a broader understanding of navigating.
Okay.
Like reaching a point teaches efficient path planning. The no-goal exploration task forces it to learn safe wandering and obstacle avoidance. Training on all these makes the final policy much more robust and adaptable for different real-world needs.
It's really clever how they leverage the perfection of the simulation, that complete knowledge, to train something that works with the limited, messy view of the real world, like learning the rules of the road in a perfect simulator before you drive a real car in traffic.
Exactly that. And the sheer scale of that simulated data, 363 kilometers, 56,000 paths, 10 million images. That's just a massive amount of experience for the AI.
Yeah.
Far more than you could realistically collect with physical robots.
It really sounds like this NavDP approach is a big step up from maybe more traditional navigation methods, like the ones that build maps first.
Yeah, the paper compares it. Traditional methods often build a map, then use something like a search to find a path.
Right.
But that could be slow, computationally heavy, and if the map's wrong or incomplete, or if things move around a lot, it struggles.
Dynamic environments are tricky.
Very. NavDP, because it's this end-to-end learned policy, it just reacts.
Yeah.
It makes decisions really fast. They mention over 10 hertz inference speed.
So it can react to things happening right now.
Exactly. Moving obstacles, unexpected changes. And their tests showed it generalized better across different robot types compared to some of those planning methods, too.
It really feels like NavDP could be a significant leap, making robots more versatile, easier to deploy in the real world. Training cheaply in sim, then just working on different robots, different places. That's a big deal.
It holds huge promise. And those early results with Gaussian splatting for the real-to-sim tuning, that points towards maybe closing that sim-to-real gap even more without losing the generalization.
Right, make the simulation look even more like reality.
Potentially, yeah.
Yeah.
Get the best of both worlds.
Okay, so just to quickly recap what we've covered in this deep dive on NavDP. It's a new way to teach robots navigation, trained only in simulation.
Correct.
It uses diffusion models to generate lots of path options and a critic function to pick the safest one.
Mm-hmm.
That privileged information in the sim is key for creating a huge high-quality data set
Right.
really efficiently.
Very efficient, yeah.
And the big payoff, impressive zero-shot transfer. It works on different robots in real environments without real-world training.
State-of-the-art results there.
Plus, that early look at using Gaussian splatting for real-to-sim tuning looks promising for boosting real-world success even more.
Definitely something to watch.
And it does all this while being faster and, in some cases, better than older methods.
Outperforming previous approaches and offering that real-time capability.
Right, and that data efficiency is worth hitting, again, 2,500 trajectories per GPU per day.
That's how they got that massive 363 kilometers, 56,000 trajectories, 10 million images data set.
Yeah.
Just not feasible in the real world.
And they really showed it worked on different robots, the Unitree Go2 quadruped,
The ClearPath Dingo wheeled robot.
and the Galaxy R1 humanoid, in simulations of hospitals, offices, warehouses, plus those real-to-sim scenes.
Broad testing.
And they used standard metrics to prove it worked, right? Things like episode time, explored area, and success rate, and SPL for goal navigation. What's SPL again?
SPL is success rate weighted by path length. Basically, did he get there and did it take a good, efficient path?
Efficiency matters too.
Definitely. And NavDP scored well across the board in both sim and real-to-sim tests.
They also did tests taking parts out of the system, didn't they? To see what mattered most.
Yeah, ablation studies. They showed that critic function was really crucial, both for training and for picking the safe path at runtime.
Okay.
And also that multitask training, teaching it different navigation goals, was essential for making it so adaptable.
And it wasn't just simulations. They put it on actual robots. Unitree Go2, Galaxy R1, Unitree G1.
Yep, real hardware.
In real places with moving people.
Indoor-outdoor scenarios.
Yeah.
Dynamic obstacles.
Yeah.
And even with differences like camera views, lighting changes, and motion blur, things you get in reality,
Yeah.
the policy still managed to find safe paths.
That's impressive. And that trade-off with the real-to-sim data a little bit helps a lot, but too much hurts generalization.
Yeah, suggests a sweet spot. Use just enough realistic data to fine-tune for the real world, but not so much that it forgets how to handle completely new things.
They also compared it directly to a planner called Ego Planner.
Right. Showed NavDP did better on diverse robots and had that real-time speed needed for dynamic scenes. Over 10 hertz on a laptop GPU, even with the robot moving up to 2 meters per second.
Of course, no research is ever finished. The paper mentioned limitations, areas for future work.
Sure, they noted it doesn't understand language instructions yet, so you can't just tell it go to the kitchen.
Okay.
And it doesn't explicitly model the robot's own shape, which might be tricky in very tight, cluttered spaces. The camera might see a gap the body can't fit through.
Right, physical constraints.
And finally, it outputs trajectory commands, so it still needs a separate low-level controller to actually make the robot's wheels or legs move.
Got it. So still steps to take. But overall, this research really gives us a glimpse, doesn't it? A future where robots learn complex skills like navigation in virtual worlds, and then just apply that knowledge here in our messy reality.
It's a powerful idea.
Think about the implications, More versatile service robots, maybe. Autonomous systems that can just go into totally new places, disaster zones, maybe without needing months of real-world training first.
The possibilities are huge.
So what new doors does this kind of sim-to-real learning really unlock? For robotics, and maybe even beyond. Something to think about.